So deep learning is actually one very powerful family of machine learning models compared to the previous models we have introduced. One of the important features of deep neural networks is basically you are trying to integrate prior knowledge on the local global dependency of the systems or process you are trying to model so that you can derive better prediction using those deep neural network architectures. And as I already mentioned, the first generation of artificial neural networks is a classic multi-layer perceptual neural networks. Essentially, you are going to concatenate fully connected layers of perceptrons as artificial neurons. And if you have more than two hidden layers, then you actually also have the deep neural network model. But all the layers in your deep neural network are fully connected, so it may not capture the dependency in the best way. And of course, deep neural networks has been popular almost for a decade now. And before I talk about different families of deep neural networks, I want to kind of mention the recent advances in deep learning. And one of the important research directions for deep learning is to derive deep generative models. So actually, we did not talk too much about the difference of discriminative and generative machine learning models in the past lectures. So the difference of discriminative and generative models are essentially whether you can use your model to simulate or synthesize the input feature vectors conditioning on the output labels. So actually many machine learning models may not have this capability. For example, if we do the logistic regression is a model based on the conditional probability of output label given input feature. If you do not construct a Bayesian model to specify the prior distribution of the input features, then it is difficult to generate the input features within the certain class. So it's actually a discriminative machine learning model instead of a generative machine learning model. On the other hand, there are also generative models, essentially many Bayesian framework. If you are trying to develop the machine learning models in the Bayesian framework, then typically they can be generative. And of course, the generative models may not be necessary to be in the Bayesian framework. Probably many of us have heard about two important deep generative models. One of them is so-called variational autoencoder. A variational autoencoder is a Bayesian model. So basically, if you look at the schematic illustration of the variational autoencoder, essentially you have the input features, and then what you are going to do is to train an encoder or a encoder network or a projection network which can derive the latent representation of the given input features. And at the same time, then you have an inference network or decoder given the latent representation, then you can reconstruct the input features. Now, if you have some output labels, then of course you can add the prediction branch so that you can make the features somehow incorporate the functional relationship with respect to the target outputs. And on top of that, then you can also do the conditional variational autoencoder so that you can generate the corresponding input features given either some condition or some desired target output. If you look at this, then you can see that essentially the important thing is that you want to model those distributions. So encoder has a kind of variational distribution, and decoder have the likelihood distribution. With the distribution of the input features, then you can write out the objective function as a Kullback level divergence to approximate the actual posterior distribution of the latent representation given the input features by this model setups. So after that, then you can do the end-to-end training to make sure the latent representations can capture the distribution of your input features very well. So that's essentially the very high level introduction of variational autoencoder idea. So you can see that actually because you are worrying about those probability distributions, so essentially this is actually a Bayesian paradigm for the deep generative models. And then another very famous deep generative models is known as generative adversary network model. So generative adversary network again is not a Bayesian. Actually, it's based on a game theoretical formulation. So basically what you are trying to do is to have a generator given some latent representation or given some conditions. Through this generator neural network or the functional mapping, you are trying to come up with some input feature generation or simulated input features. And then what you are going to do is to compare those generated simulated input features with actually available observed input features. You're trying to compare them to see whether the generated features have similar patterns, similar characteristics of the observed training data set. Basically, you are trying to have a discriminator to tell the difference of your simulated or generated input features and the real world observed input features. So you basically formulate a game theoretical formulation so that the discriminator and the generator are helping with each other so that you can generate better input features, and discriminator can help you to improve the quality of generated input feature vectors. And of course, you can also extend it to include the target labels by introducing the conditional generative adversary network model. And those are actually two models that have been developed and improved in the past 5-6 years. And more recently, there are two other deep generative models. One is known as a flow-based model, and the other is more recent diffusion-based model. So both of them are actually trying to, again, use the basic probability theory to help you to learn the distributions. So basically what we are trying to do is to learn a flow model, f of x. This flow model is essentially doing the transformation of the original input features to your latent representation. And then because you have the transformation, so this latent representation, you can make some assumption on its distribution families. For example, one of very commonly adopted distribution for this latent representation is Gaussian distribution. Of course, you can use other like parametric distribution families besides the Gaussian distribution. But if Z is a Gaussian distribution, and if you consider X, you somehow transform the random vector X to achieve the Gaussian distribution. And then when you do the inverse transformation of the Gaussian random vector, then you will have the transformed random vector x prime. And then depending on the function form of this inverse transformation, then the distribution of this generator random vector will take different types of distribution families. And it depends on the complexity, expressiveness of your inverse transformation of your flow-based model, then you can achieve desired distribution properties. For example, you want to have multiple modes instead of only having single mode if you have the multivariate Gaussian distribution. And also if you want to have the heavy tail distribution of your random vector, then what you can do is to change the flow-based model function f to achieve those desired distribution properties. And besides that, if you kind of reasonably set the flow model function mapping into the neural network forms, then given the observed training data, then you can use this flow-based model to approximate the data distribution that you observed in your training samples. So this is a flow-based model. So the difference of flow-based model from the variational autoencoder, instead of have this encoder-decoder structures, now you only need to worry about this flow-based functional models. And if you assume that it's invertible, then you can do the end-to-end training to derive a distribution, and the distribution of the generated data points will capture the observed distribution of your training samples. So that's a flow-based model. A more recent deep generative model is known as diffusion models. Essentially, you can consider diffusion models as the extension of flow-based models. The idea is essentially quite simple. So basically, assuming that x0 is input feature vectors you observe, and you are trying to understand the distribution of those input feature vectors. So what you can do is to do the diffusion process to this observed input random vector. And basically, if you are trying to add a Gaussian noise into those random vectors gradually, and if you add more and more Gaussian noise at the end, you will end up with a isotropic Gaussian random vector Z. So this is the procedure from your training set. And then now what you are trying to do with those diffused random vectors, what you are trying to do is to learn a neural network model which captures a reverse diffusion process. Basically, what you are trying to do is to use those diffused random vectors to train the neural network models from this isotropic Gaussian random vector to recover the observed input feature vector. If the diffusion process give you the Gaussian random vector, and then when you sample this Gaussian random vector going through this learn or train the neural network model, then hopefully the distribution of the generated input feature vectors capture the distribution properties of the input feature vectors in your observed training sample. So that's essentially the basic idea of the diffusion models. And of course, if you want to understand all those 4 different types of deep generative models, there are textbooks and research papers. You may have to look deeper into them to understand all the fundamental mathematical basics. So why we talk about deep generative models? The reason is that I mentioned early, when deep neural network works, you basically need to have a large amount of training data to make sure your deep neural networks are trained, converged to capture whatever underlying input-output relationships, etc. So often in reality, actually, you don't have enough training data. So if you can basically develop some reasonable generative models which can capture the underlying distribution relationships in the problems of your interest, then you can use those simulated data to help you train your deep neural networks better. So that's essentially the 4 different types of deep generative models, and this is actually very active research field in deep learning. And if you're interested in any of these topics, you should read more papers, etc. And of course, there are many research directions in deep learning. Another important research direction is so-called automated machine learning or neural architecture search. So if you want your deep neural networks to work better, then you need to capture the global local dependency, etc. So multiple layer perceptron may not necessarily capture all the local global dependency. Then people think like how I can use the data to learn the best connectivity patterns or architecture of my neurons in the deep neural networks. So this is one active research area, again, trying to automatically design the neural network architecture for the problem of interest. Now, we will not talk about that. Again, you should look for the papers on this topic and try to understand better. So here we are basically going to have a brief overview of existing deep neural network architectures based on the problems on the study. The first, probably the most famous deep neural network architecture is called convolutional neural networks. So what is convolutional neural networks? If we use image analysis as a problem on the study for the example, then basically convolutional neural networks, instead of looking at fully connected neurons for all the input pixels in the image, we are going to design the neurons only based on the local neighborhoods. The reason is very natural because, like, for example, if you go with the neuroscience point of view, then the visual fields is limited. You do not necessarily do the, say, object recognition based on the whole image, but you are going to look at the local neighborhoods to decide whether this is a robot hand or not. the visual fields are actually having this local dependency structure. When you design the corresponding artificial neural networks, you want to capture this local dependency structure. So instead of deriving features across whole image, you are going to deriving the intermediate features or hidden representations in the local fields. And how do you derive these hidden representations based on local fields? You are going to define the convolution operators or filtering to only looking at the linear combinations of the pixel values around these local fields to determine the hidden feature values. So you keep doing that. If you are going to do the deep neural networks, multiple layers, you're still trying to capture the local fields. And also when you go deeper and deeper, then those derived hidden representations at the same time also capture the global information. So by this kind of design of convolution neural networks, then hopefully you can capture both local and global dependency information and give you better predictions. Of course, this is on using image analysis as an example, but convolution operators or convolutional filters can be designed up to high dimensional space, not necessarily two-dimensional space, right? It could be three-dimensional space, it could be four-dimensional space, it also can be one-dimensional space if you are looking at the temporal dependency structures. So indeed, the convolution neural networks are used in both image analysis, natural language processing, and temporal spatial process related applications. And then the second important deep neural network architecture is known as a recurrent neural networks. And recurrent neural networks is essentially trying to capture the temporal dependencies. This is like one aggregated representation of a recurrent neural network. Now here, basically you unfold this aggregated recurrent neural network schematic. So basically you can see that this latent or hidden representation at each time point is going to be dependent on the previous hidden representation at previous time points. This is essentially very vanilla representation of recurrent neural networks. Why this is interesting? This is interesting because this dependency structure across different time points can be captured in this recurrent architecture. What happened in the history will be determining your belief on what are going to happen in future. So if you can capture this historical dependency better, hopefully you can derive more robust and accurate predictions for future. So that's essentially the idea of a recurrent neural network. And of course, like what I said, there are multiple different recurrent neural network architectures. Two most famous recurrent neural network architectures include the gated recurrent unit, GRU type of recurrent neural network architecture. So essentially, this is basically trying to capture the dependency structure more flexibly so that you can even capture the high order relationships across different time points. And then another important recurrent neural network architecture is so-called a long short term recurrent neural network. And again, it introduces another latent variable or hidden variable CT-1 here, in addition to the hidden representation to capture the higher order temporal dependency structure better. So that's pretty much two important recurrent neural network architecture, but both of them are basically trying to capture the temporal dependency relationship. So we will talk about the recurrent neural network in more detail a little bit later. So the third deep neural network architecture is known as graph neural network. So for both a recurrent neural network and a convolutional neural network, essentially you are looking at the input feature values at the regular grid structure. So if you are looking at the recurrent neural network, then in one dimensional, you are getting the sampled time points and look at the observed signals in corresponding sampled data points. You are trying to capture the relationships across different time points. And if you are looking at the image problems, then you are looking at the pixel grids of the image, and you are trying to use the convolution operators to capture the local neighborhood dependency relationships in these pixel grids. But in many real-world applications, actually, you don't have these regular grid structures to observe input features. So for example, if you are trying to do some like sensing applications, trying to identify, for example, in Antarctica, how the icebergs are melting. You can't really make sure when you put the sensors, it has this regular grid structure. So sometimes you do have those irregular input features sensed at irregular locations, right? And also in many real world problems, you only have very rough interrelationships across different feature types, but you still want to capture the global local dependency relationships. In this type of situations, then you basically have this kind of graph structure to capture either the special relationships or the dependency relationships. And each node corresponding to the individual features and the relationships between the edge of the graph basically capture the either special relationships or dependency relationships across different features. And then what you are going to do, for example, if you are trying to say, since the features, then we are going to do the classification saying that we have the global warming situation or not. For example, it's just a fake example. And so what you are going to do, again, like image classification, image analysis, you are trying to utilize or derive latent features or hidden representations of all the observed sense melting status in different places in Antarctica, and derive the hidden features. And then if you want to do the deep learning, then you add multiple layers to better fuse those hidden features to capture the global relationships. And at the end, then based on those diffused features, and then you are going to do the classification task. So that's essentially the graph neural network architecture. The difference of graph neural network from convolution neural network and recurrent neural network is that the relationships of each input features or latent representations are having this irregular graph structure. And in fact, the derivation of the hidden representation values are essentially a diffusion process, or you can use the Markovian random walk model to model this derivation of the hidden representation values. And also a related research field is known as graph signal processing in stochastic signal processing community. There are many mathematical underlying similarity of graph signal processing and deep learning using graph neural networks. And if you are interested in these topics, then you can again search for the graph signal processing papers. You can read more graph neural network papers. This is basically two actually wiki pages that you can look into if you are trying to understand better about the deep generative models. So in one of actually interesting research direction is to do the deep generative models using graph neural networks.